All right, part two. We are investigating the relationship between ionization energy and these electrons. So once again, what they thought was that as you take more and more electrons from an atom, it's going to get smaller and smaller and smaller. As it gets smaller and smaller and smaller, because of Coulomb's law and the relationship with distance, right? As it gets closer and closer and closer, the energy is going to go up and up and up. What they thought was that the graph would look something along these lines. And like I said in the last one, they were mostly right, but they were a little bit wrong. When they actually did the experiment, it actually turned out to be something like this. Now, wait a minute. Take a look at that. Here's your 7 ionization energies for nitrogen. 1, 2, 3, 4, 5, 6, and 7 that are there. And yeah, they're going up. But what do you notice? Well, there's this big split that's here. And they went, what's up with that? And so they began to do experiments on all of the elements to see what they looked like. So let's examine some others. So let's start, if we could, by looking at the periodic table. And again, you should have the periodic table with you. It's going to make things a little bit easier to see what's going on. It's going to explain a little bit about why the periodic table is arranged as it is, too. But let's start here, and let's start with lithium and work our way across the periodic table until we hit neon over there. So lithium, by the way, has 3 electrons. Beryllium has 4, 5, 6, 7, 8, 9, and then 10. We're going to be looking at those, right? And again, as you take more and more electrons away, it should go up and up and up. So here's lithium. All right, well, that looks pretty normal, right? That looks like it should. So maybe we have more here. Here's beryllium with its 4. Well, wait a minute. That's kind of a straight line, but really you could also interpret this as kind of 2 and 2 here, all right? Here's boron. Oh, yeah, we should definitely be doing that because now I've got 3 and 2 for our 5, all right? So our next one is 6. That's going to be 4 and 2, right? For our 6. What do you think 7 is going to look like? Oh, wait, we did that one already. That's nitrogen. That's 5 and 2. What do you think our next one is going to look like? Well, that's oxygen. That's 6 and 2. That's there, right? And then what about our next one? Fluorine. Yep, 7 and 2. And then finally, neon, 8 and 2. So apparently, if you go from 10 all the way back down to 3, there's 10 at 2 and 8. There's 9 at 2 and 7. There's 8 at 2 and 6, 2 and 5, 2 and 4, 2 and 3, 2 and 2, and apparently I guess maybe it's 2 and 1, although it's tough to tell on that particular graph because we don't have enough data. So what is going on with this? Why is there a split with 2 and then the rest of them, right? Now take a look at your periodic table. What we just did was we looked at the second row, which was this row here on the periodic table, the lithium row. What do you think we're going to see if we do the third row for all of those across? Take a moment, pause the video, and then make a prediction. If the second row looked like what we just saw, what is the third row going to look like? Take a moment, pause the video, think about it, and then come back. All right, I'm assuming you're back. So let's take a look at what those are. So here's sodium. Oh, wait, so there's those 2 that are there. And now, again, it's tough to tell with things that are there, but because that all kind of looks like it's maybe the same. So that is that 2 and 9. Here's magnesium. Oh, wait, are we beginning to see a pattern? Here's that. And doesn't it kind of look like those are split a little there? And here's aluminum. Oh, yeah, definitely. There's a big split there and then a smaller split there, but there's still a split. Silicon, oh, definitely. 2, and then those with a split that's there. And then here's phosphorus, 2, and definitely a split that is there. And again, these ones in the middle, 1, 2, 3, 4, 5, 6, 7, 8. That should sound familiar, right? 2 and then 8 and then 5 for the phosphorus. And now here's sulfur with 2 and then 8 again here in the middle, right there, and then 6 there for the sulfur, right? And then chlorine, 2, 8, and 7, and then finally here neon with 2, 8, and 8 that is there. So here's neon with 2, 8, and 8, 2, 8, and 7 for chlorine, 2, 8, and 6 for sulfur, 2, 8, and 5. Again, 2, 8, and 5 for phosphorus. Here is silicon with 2, 8, and 4 for silicon. Here's aluminum with 2, 8, and 3 for that one. Here's magnesium with 2, 8, and 2. And tough to tell on the sodium, but apparently it's 2, 8, and 1 for the sodium. So again, we got 2, 8, and 1 there with those 8 in the middle. 1, 2, 3, 4, 5, 6, 7, 8. That is there. All right. So basically what they determined was that all of these electrons are not just randomly placed out there, but they're in groups. And those groups apparently come in different numbers. Apparently there is a group here of 2, there is a group of 8, and now there's another group of 8 that's there. So what we've got here, again, here's the same data but a different look that's there. We see a huge jump after the 8th that's there. We see a huge jump in the ionization energy after the 16th that is there. And then we've got those last 2, so we've got 2, 8, and 8 here. Every one of them is increasing, but sometimes there are then these huge jumps that tell us that the electrons are not all equal. They are in different places, or what are called different shells, right? So this is one shell, this is another shell, and this is a third shell. And apparently you can fit different numbers of electrons in these shells. So you've probably seen this before. Rutherford said, oh, they're all just kind of out there, whereas in reality, this is really more along the lines of what we're looking at. So fluorine has 9 electrons. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. But those 9 electrons are not all equal. Apparently, there are 7 electrons on the outside that are the easiest to take for fluorine, and those are the first ones that we're going to see here because they're the easiest to take. And then I've got 2 more here that are on the inside on an inner shell that are those 2 up there. Those are even closer than the other ones, and so that's why, according to Coulomb's law, they are the hardest to take. So this inner shell, or shell 1 here, is our first shell. That's those electrons that are there. And then we've got an outer shell that are further away from the nucleus. So as distance increases, energy decreases. That's those electrons that are there. So we see a shell model. So take a moment, pause the video. What do you think the electron arrangement for chlorine is going to look like? Find chlorine on the periodic table. Pause it and give it a look. All right, I'm assuming you're back. Here's chlorine. There are 17 electrons for chlorine, but they are going to be fit into the first shell, which has 2. That's our first shell. And then a second shell, which has up to 8 in it. That's our second shell. And then our outermost shell, which are these guys here, which are these 7 that are going to go there. So chlorine has 3 shells, a 2 shell, an 8 shell, and a 7 shell. Take a look at the arrangement on the periodic table. Check it out. Here's the first 2 electrons of the 17 here. Those are elements 1 and 2 on the periodic table. You'll notice that they're in the first row, or they are in shell 1. Shell 1 is that first shell. There they are. Now your next shell has 8 electrons in it. Not a surprise then that on the periodic table we've got 8 elements in that shell. 1, 2, 3, 4, 5, 6, 7, 8. And you can fit 8 electrons in the shell around it, and there they are. There are those 8 electrons. And then that shell is now full. So now we got to go to a third shell, or the third period. And there are apparently 7 electrons for Chlorine in that one. 1, 2, 3, 4, 5, 6, 7. And here they are. And they are the easiest ones to take because they are the ones that are on the outside of the atom. And again, the ones on the outside are considered to be the valence. So these are the valence electrons. The valence are ones that are on the outside of things. So if we go back to these examples here, any one of these that we look at, here's neon, for example. Neon has these that are in the valence, and it's 1, 2, 3, 4, 5, 6, 7, 8. So neon is in the 8th valence, which is why it's not surprising. It is, if we check the periodic table, here we are, it is in the 8th column. 1, 2, 3, 4, 5, 6, 7, 8. Although if you check your periodic table, they typically do it in Roman numerals. So it'll be 1, 2, 3, 4, 5, 6, 7, and 8. You'll often see that for the periodic table. Neon has 8 valence electrons, which is why it is in the 8th column here. Not surprisingly, lithium has only 1 valence electron, which is why it is in the 1st column that's there. Beryllium has 2 valence electrons. Again, the outermost are the valence electrons. So not surprising that beryllium is in the 2nd column. Now, boron has 3, 4, 5, 6, 7, and 8 back up to neon there, so it's not a shock then that boron has 3 valence in the 3rd column. Carbon has 4 valence in the 4th column. Nitrogen has 5 valence in the 5th column. Oxygen has 6 in the 6th column. Fluorine has 7 in the 7th column. And now here we go up to neon, 8. And apparently at these early levels, the maximum you can get is 8, which is why we call this the octet rule, right? The octet rule says it is 8 maximum in a shell. It's not quite true because apparently in the first valence you can fit 2. And we'll discover with subshells and everything later like that, you can go further than 8, but now we're getting complicated. So, anywho, taking a look at the first 18 where things are nice and neat and regular, this is your first shell that has 2. This is your second shell that has 8, and this is your third shell here